Thanks a lot, Professor Muller, uh, for inviting me here. And I must thank the organizers for inviting for this wonderful conference. Initially, actually, I had a plan to come and deliver this talk in person, but due to my actually some schedule, I couldn't able to come there to Paris. So my talk is actually based on functional heterojunctions, nanocatalysts for scalable hydrogen production. Since actually the time is quite short for this presentation, only 20 minutes is allotted to me. So actually I will skip the brief part of my presentation, like actually when we talk about the nanocatalysis or the nanomaterial, everyone is known about actually the nanomaterials are fine materials having grain size 1 to 100 nanometers. Nanostructures having different geometries like rods, wires, tubes, cylinders, bipods, tripods, tetrapods, nanotubes. If one of their dimension is in the nano range, the nanowires, core shell nanostructure. So basically, actually, the nanomaterials could have show drastic applications like some unusual properties like the confinement of electrons, high surface area, and large number of electric or magnetic dipoles disordered at the surface. So because of these unusual reasons, the nanostructure could find applications in electronic devices, memory devices, catalysis, sensors, and energy. So today I'm going to speak, covering the two parts, catalysis and the energy. So actually, when we reduce the size of the object, actually the surface area is an important property when we talk about the materials property or the application under catalysis. So when we reduce the size of the objects, the surface energy will increase or the surface area will increase. Here actually I have shown one of the schematic presentation as well as the mathematical calculation, how to calculate the covered area. And here actually I have shown you can easily calculate the covered area of 2 centimeter edge length cube. Its covered area is 2 into 2 and multiply with the number of surfaces means 24 square centimeter. And if you actually cut down this 2 centimeter cubes, you can extract 1 centimeter cube. The number of cubes will be 8 actually. And the covered area of these 8 number of cubes having edge length 1, it will be actually 8 into 6 into 1 into 1 means 48 square centimeter. So just you can actually have a very smaller comparison that actually if you reduce the size of the cube from 2 centimeter edge length to 1 centimeter edge length, the covered area will increase from 24 to 48 square centimeter. So, but actually when you play with the materials at the nano dimension, actually you reduce the size of the object nearly 1,000 times. So you can actually correlate actually how in the bulks, but in the comparison of the bulk, actually how many times the surface area will increase, because this is the important property of the material when you talk about the nanocatalysis. Actually, nanocatalysis is having various components. So, but I am actually working at my place based on the organic transformations, photoelectro and the photoelectrocatalysis. Actually, millions of the organic conversions already known, which were actually supported by the inorganic material means inorganic catalyst. But if you transform all the sizes of the inorganic catalyst into the nano dimension, then this area actually having a very huge potential. Actually, then you will have the millions of the organic nano transformations reactions, because actually these transformation can produce a variety of the medicinal products which are industrially viable compounds. And when we talk about the catalysis mechanism, generally there are 3 steps which are actually involved in this type of the reaction: adsorption, reaction, and the desorption. During adsorption, actually the reactant molecule adsorb at the surface of the catalyst. So if the catalyst is in the nano dimension, then it has a very vast surface area. So large number of the reactant molecules can get adsorbed at the surface, where actually the bonds are broken or reformed to form the reaction, and finally they dissolve into the final product. So actually we have designed a number of the metal oxide which are having a very beautiful structures, and we have actually applied all these metal oxide based nanocatalysts for many of the organic conversions involving oxidation, hydrogenation, amination, carbon-carbon coupling, and the electrophilic cyclization. Published a number of the papers mainly on this concept. But today I'm going to speak about the water splitting. Basically, in the water splitting, this is a simple chemical reaction where you break water molecule into the elemental hydrogen and the oxygen. But this reaction actually, the breaking of or the water splitting, generally it requires the presence of the two driving forces. One is the actually light source, and other is the catalyst presence. So the simplest source of the light is the actually sunlight, and if we see the solar spectrum of the sunlight, then actually its maximum component is the visible light component, which is around 46%. So we need to design the material which are visible light active. So we and the material which will be visible light active, it will have the optical band gap in the range of 1.8 to 3.2 electron volts. So we need to make some chemical modifications either by doping off the metals or the metal oxide post lattice, or by designing the heterojunctions or heterostructures, so that actually we can tune their optical band gap and having the small grain size, so that actually they will have the high active catalytic side, which actually promotes the photochemical conversion reactions. So during in this conversion, actually the hydrogen is produced. So why we have so much interest in the hydrogen? Because actually, if you see globally, you could see the energy of the crisis worldwide because of actually a number of reasons like overpopulation, poor infrastructure, overconsumption. So hydrogen actually is considered as the sustainable or the renewable energy, and it can actually overcome the energy crisis issues, because the hydrogen is considered as the clean fuel of green energy. It is carbon free, highly abundant, and has zero impact over the environment. So we have actually having very much thrust over the green hydrogen production by using the overall water splitting. Actually, for overall water splitting means actually we generally adopt the photochemical water splitting, electrochemical, or the photoelectrochemical water splitting, and all these phenomena collectively called as the overall water splitting. So here actually this is the actually experimental methodology for the hydrogen production by using the photochemical water splitting phenomena, where actually first you need to actually prepare the material, then you mix with the required amount of the water, and then mix with the sacrificial agent, and then evacuate actually the means you have to produce the inert atmosphere, then you expose your solution with the light source, and you have to actually fix the wavelength of this light, so that actually the particle intensity actually can irradiate your sample, and actually then it can give the holes over the valence band and the electrons in the conduction band. And this actually electron hole pair recombination, it should be actually discouraged, because we must have the actually free electrons over the conduction band, which are actually used for reduction of H plus into the hydrogen gas. So basically these photo-generated electrons are used for in the hydrogen production. So and these actually the whole structure actually is used to is actually occupied by the sacrificial agent. The another methodology is the electrocatalytic water splitting. So we actually electrocatalysis is the simplest method which is known for the water splitting. Here actually we use the direct current for the separation of hydrogen and the oxygen. Here actually there are the two electrode system on hydrogen evaluation reaction occur at cathode, whereas the oxygen evaluation reaction occur at anode. These are the half cell reaction, and the complete cell reaction is written over here. The third methodology is the photoelectrochemical water splitting. So basically, both the methodologies are same actually, electrochemical and photoelectrochemical. The only difference is that actually in the photoelectrochemical water splitting, we have to use the light source. So actually for that actually you need to design the cell assembly, which is actually friendly to be exposed by the light source. So this is the actually difference. So we have actually I have set up all three methodology in my research lab there in New Delhi, Jamia Millia Islamia, and we are actually producing very interesting and the good results. So here actually I'm showing the graphitic carbon nitride material, because actually graphitic carbon nitride is a very interesting material because of its actually optical band gap structure, and actually graphitic carbon nitride is an ideal candidate for photocatalytic water splitting due to its excellent alignment of its band edges with the water redox potential. So anyone actually can easily prepare the graphitic carbon nitride by taking the melamine, and if you anneal melamine around 520 degrees centigrade temperature, then it can produce the bulk graphitic carbon nitride. And if you exfoliate this bulk graphitic carbon nitride in sulfuric acid or which HCl, then it can produce a very beautiful nano sheets of graphitic carbon nitride, which are having the honeycomb like highly porous structure, which can be easily visualized by actually here. Actually, you can see with the help of the electron microscopic images and the tilting of the sheets, you can easily see during the exfoliation in the FESEM images. So before going to the actually photochemical water splitting measurements, we generally go for the basic characterization, like we do the X-ray diffraction, we go for the surface area, UV-DRL studies, we go for Raman, we go for actually XPS, PL. Actually, we do a number of the measurements for investigating the material in detail. Then we go for finally the application part. So for this the water splitting measurement, we have actually made two different set of reactions. In one set of reaction, the trithenolamine was used as a sacrificial agent, and in another set of reaction, the sodium sulfide and sodium sulfide was used as the sacrificial agent. And we have observed that the trithenolamine can generate 470 micromole per hour per gram of hydrogen, whereas actually with an apparent quantum yield of 12%, whereas actually this sodium sulfide can generate 230 yes, this one, yeah, micromole per hour per gram of hydrogen with an apparent quantum yield of 7%. Then this is the actually detailed investigation of the photoelectrocatalytic studies. This is the LSU plot for the HER investigation. This is the LSU plot for OER, and this is Truffle slope and the turnover frequency plot. So these actually, this one actually HER and the Truffle slope plot shows the low onset potential, which is actually associated with the high photocurrent density, which requires actually very less voltage for the hydrogen generation. And actually the intrinsic activity we have also calculated, and actually it gives the Frederick efficiency, which is very close to actually 100%. So we have reported these investigations for the first time about the graphitic carbon nitride in the literature. So we took actually this graphitic carbon nitride and we have designed a number of the heterojunctions, one with the actually copper ferrite. So we have actually made copper ferrite nanoparticles by using the hydrothermal method, and we have mixed this copper ferrite with the graphitic carbon nitride by mechanical mixing, and we have prepared the graphitic carbon nitride heterostructure. So we have the mixing actually is done in 10, 20, 30 weight% ratio. And here actually if you have the very good understanding about the X-ray diffraction and other actually X-ray diffraction, then you can actually easily index each and every wave that we have actually done, and go for other primary investigation actually techniques. Then coming for the water splitting measurements. So for that actually catalytic water splitting, we again actually made two different set of reaction, one with the trithenolamine as sacrificial agent and other with the sodium sulfide as sacrificial agent. And this actually 28% loading of the copper ferrite over the graphitic carbon nitride can produce 1 millimole per hour per gram of the hydrogen by using the trithenolamine as the sacrificial agent with an apparent quantum yield of 25%. So whereas actually the high loading of the copper ferrite nanoparticles over graphitic carbon nitride can likely reduce the light absorption by highly porous graphitic carbon nitride nanosheet, thereby decreasing the formation of the whole pair structure. And actually the best result that we have obtained by using the trithenolamine as a sacrificial agent because of the actually non-polar nature of both the catalyst as well as the sacrificial agent, which actually increase the wettability of the catalyst surface. So here actually this is the charge transfer dynamics. So in the first plot actually this is the electronic impedance spectroscopic plot, which shows the low charge transfer that leads for the enhanced interfacial charge transfer on the surface of the heterojunction. Whereas the actually more Schottky plots for the pure phases of the graphitic carbon nitride, copper ferrite, as well as for the heterojunction. So here actually if you see, then you could see actually the positive mode Schottky plot showing the N type of the semiconductivity for graphitic carbon nitride, whereas for copper ferrite, actually it gives the negative mode Schottky plot, which show the p-type in semiconductivity in copper ferrite. Whereas actually in the mixture, means heterojunctions of the copper ferrite with the graphitic carbon nitride, it gives the positive as well as the negative mode Schottky plot, which shows the PN heterojunction formation for copper ferrite with graphitic carbon nitride heterojunctions. So in the detailed PL investigation, actually it shows that there is actually decrease in the PL intensity, which suggests the low recombination of the electron-hole pair. And here actually, if you see the best result for the electron-hole pair recombination is for the actually 28% loading of the copper ferrite over graphitic carbon nitride. And in fact, this 28% loading of copper ferrite over graphitic carbon nitride can give the best result for the photochemical water splitting hydrogen production. And here actually this is the band structure mechanism before the mixing of copper ferrite with graphitic carbon nitride and after mixing. So when actually after when you actually mix copper ferrite with the graphitic carbon nitride, then actually the Fermi level alignment occur, and during the Fermi level alignment, the electrons that are present in the conduction band of the copper ferrite tunnels to the conduction band of the graphitic carbon nitride, which are actually used to reduce H plus into the hydrogen gas. So this is the actually electrochemical investigation for hydrogen production. So here actually you could see this is the LSC plot for the OER, and the corresponding Tafel flow plot is shown in the right hand side, whereas this is the LSC plot for HER, and the right hand side you could see its corresponding Tafel flow plot. So both actually investigation shows the improved current density and lower overpotential of the copper ferrite graphitic carbon nitride heterostructures, which reveals that the copper ferrite nanoparticles can not only actually increase the charge transfer but also increase the active site for water splitting reaction. And we have also actually reported the maximum Faradic efficiency for these heterostructures. So another actually heterostructure that in this series that we have reported very recently, this is based on the copper oxide with the graphitic carbon nitride, and it shows the type 2 mechanism that we have actually proved by using the actually DFT and other theoretical investigations. So here actually copper oxide nanoparticle we have prepared by using again the simple hydrothermal assembly, and we have mixed them mechanically here actually, and by using the investigations of X-ray diffraction, we have indexed and get the correct information about the copper oxide graphitic carbon nitride monophasic heterostructures, and calculate the surface area and the band structure to explain the high catalytic activity of these heterostructures, and to actually get the nature of the light source. So actually among the DFT calculations, actually in the DFT calculation, we have shown that the copper oxide and the graphitic carbon nitride both having the different structure. So during the DFT calculation, first actually when we index into the same structure, then the conduction band of the graphitic carbon nitride become more populated, and which is responsible for high hydrogen production rate by using the heterojunction, which is shown over here in this slide. So here you have shown that the 38% loading of the copper oxide over the graphitic carbon nitride can produce 3.5 millimole per hour per gram of hydrogen with an apparent quantum yield of the 18%. So in fact, we are the first in literature who have reported this much actually significant result by using these heterojunctions. So in the actually very interesting result we have obtained when we do the electrochemical investigations like HER and the OER, and we have compared all our results with the commercially available iridium oxide, which is a very popular material, and we have observed that most of the parameters in our study either are better than the iridium oxide or are comparable to the iridium oxide. So we have shown in the literature the possibility that our as prepared copper oxide with graphitic carbon nitride heterostructure could be the actually best replacement for the commercially available iridium oxide in the electrochemical investigation for the hydrogen production. So here actually very interesting results that we have actually reported in the literature that we have published in a very reputed journal, that is the AC's Catalysis. Here actually we have designed the cadmium selenide quantum dots. In fact, actually we have grown these cadmium selenide quantum dots over graphic carbon nitride nanosheets by using the CELAR method. So in the CELAR method, actually we have run the CELAR cycles as 10, 20, or 30, and we have named all these actually combinations of these heterojunctions as 10, 20, or 30 cadmium selenide CELAR cycles or the quantum dots over graphic carbon nitride. And actually we have investigated these material by using n number of the investigations, like we do the electron microscopic study, the X-ray diffraction, XPS, PL, transit photocurrent, absorption spectra, many actually investigations we have done. And here actually you could see that the 30 CELAR cycles of the cadmium selenide quantum dots of graphic carbon nitride can produce 4.3 millimole per hour per gram of the hydrogen with an apparent quantum yield of 24%, which was actually supported by the PL investigations, EIS measurement, or the photo current plot that actually shown over here. So here actually you could see the detailed investigation for the electrochemical studies or the electrochemical hydrogen evaluation reaction. Then it showed that the 30 CELAR cycles of the cadmium selenide quantum dots heterostructures with graphic carbon nitride show a significant electrochemical HER reaction, which was actually supported by the electrochemically active surface area. Then we have actually prepared the cadmium sulfide quantum dots that we have grown over the graphitic carbon nitride nanosheets, and we have actually shown in the literature the significant results for photocatalytic and the electrocatalytic hydrogen evaluation. So we have done the primary characterization for these heterostructures, and coming to this actually important part, that is the hydrogen production. So the 30 Silla cycles of the cadmium sulfide or graphitic carbon nitride can produce 14.8 millimole per hour per gram of hydrogen with an apparent quantum yield of 28%. So, and the stability of the catalyst actually we have also observed by when we run the stability test. And here actually in the HER and the OER investigation. So the interaction between the graphitic carbon nitride and the cadmium sulfide quantum dots can play a crucial role for spatial charge transfer on heterojunctions of material, which improve the catalytic activity. So we have obtained the best results of the 30 Szilard cycles of cadmium sulfide quantum dots over graphitic carbon nitride. Then, now coming to the next heterojunction, that is the molybdenum sulfide nanoflower that we have deposited over graphitic carbon nitride. So these beautiful nanoflowers of the molybdenum sulfide we have prepared by using the hydrothermal method, and we have mixed this with graphitic carbon nitride in 10, 20, and 38% ratios. And here actually this is the synthesis protocol for the whole reaction that we have reported in the literature. And this paper actually was published in the Applied Energy ACS Applied Energy Material. And these are the actually basic characterizations like X-ray diffraction, IR, UV, electron microscopic images, surface area, and number of techniques. Actually, if you go to my papers, you will see we have used actually many techniques for the investigation of these materials. Coming to the important part, actually, the 28% loading of the MOS2 or graphitic carbon nitride can produce the 18 millimole per hour per gram of the hydrogen with an apparent quantum yield of 34%. And in every case, actually, we have also checked the stability of the catalyst before catalysis as well as for post catalysis. So in the post catalysis, we have used the X-ray diffraction, SEM, and the XPS investigation. In all the results, actually, we have reported in the supplementary information, all the papers about the stability of these material. And these are the actually electrochemical investigation. And here actually the 28% loading of the MOS2 graphitic carbon nitride was very effective for the hydrogen evolution reaction. That was supported by the electrochemically active surface area of this material. And then not only actually the graphitic carbon nitride based heterostructure, we have designed some other heterostructures like the molybdenum oxide with TiO2, MO3, strontium titanate, and published in like inorganic chemistry, Langmuir. Then you could see this is the actually serious zirconia heterostructures for effective carbon monoxide gas sensing. Not only the binary heterostructures, we have designed several ternary heterostructures like MOS2 boron nitride nanoflowers over TiO2, published in the International Journal of the Hydrogen Energy. Then very recently, actually, this paper actually just appeared, MOS2, SE2 nanoflowers with the ZNO. This is ternary heterostructure that we have shown. It actually exhibits the SST mechanism, and actually it shows the significant hydrogen production, and that we have explained by with the help of the ultra-fast charge transfer mechanism for the hydrogen evaluation, just published in the ACS Applied Energy Material. Another ternary system is the NaNBO3 CDS bismuth sulfide, appeared in the International Journal of the Hydrogen Energy. This one actually the graphitic carbon nitride multi-walled carbon nanotube and the lanthanum nickelate. This material shows the Z-scheme mechanism and actually shows the bifunctional catalytic application appeared in actually materials today sustainability. And then you could see we have actually also designed actually the multifunctional or the multiferroic oxide, which actually exhibit the ferromagnetism as well as ferroelectricity simultaneously together in a same material. Then actually this class of material is called as the multiferroic. So we have designed this multiferroic multifunctional material like JDCrO3, DYCrO3, and all these material actually we have shown very significant bifunctional actually hydrogen production by using the photocatalysis and the electrocatalysis. This is the GDCRO3 published in the applied energy material, then the DYCRO3. This is the TBCRO3 or the GDFeO3, TBCRO3, then this one actually DYFeO3 or the DYMNO3. We have also designed some doped metal oxide like the silver doped or the copper doped actually tungsten oxide and nano sheets or the nano plates that we have used for the multifunctional application, means organic transformations, photocatalysis, electrocatalysis, and the photoelectrocatalysis. The multifunctional application we have actually also reported. The same investigation is also shown over here. Now, actually, we are working in my research lab over the carbon dioxide reduction, nitrogen fixation. So we have actually published some papers like actually overview or the review in actually this one in the MTS or in the Langmuir over the ambeans or the POPs type of the material. Now, to conclude my presentation, actually, we have designed the graphitic carbon nitride as well as the graphitic carbon nitride based structures with copper ferrite, copper oxide, cadmium selenide, cadmium sulfide, or the molybdenum sulfide. And in every case, is actually all these structure show the significant hydrogen production rate and also show the impressive electrocatalytic performance. So for this kind of the work actually that I have shown over here, I must thank the hard work for my research group, actually past PhD and the present PhD scholars. And I must thank my collaborators, Professor Chari, Rowan University, New Jersey, USA, Professor Mao, IIT Chicago, Professor Al Sahri, Professor Ahmad from King Saud University, Saudi Arabia, and Professor Ingole and Professor Chaudhary from Indian Institute of Technology, Delhi. And I must thank actually, without funding, actually, you can't do that kind, you can't afford to do that kind of the work. So I must thank my funding agencies, DST, SERB, CSIR, BRNS, Spark, and of course my university actually, because actually my university is very supportive, giving me the administrative help, academic help, or the academic platform or environment in the university surroundings. So with these, I must thank the organizers and all the audience actually for patient listening for my talk and giving me the opportunity to be here. So with these words, thank you very much.